So could you wait 2 minutes, please? It's just about to finish printing.
Okay. All right. Well, I started it, but okay. No worries.
So can you put the link on top? I can't find it.
You can find the link. Okay. Just a second. I wish Google Classroom had a pin thing, right? This is not good.
Yeah.
They don't have that pin thing, otherwise it would be just perfect.
Okay, so I found it.
Yeah, it's done printing, sir.
Okay, cool. And for some reason, yeah, it is almost on the top, but that's fine. All right. So now, speaking of first in this chapter, we need to learn about certain definitions. First of all, the definition of a mole for 2 marks. The first mark is always when you write amount of substance. And basically it means that which has the same number of particles as there are in atoms in 12 grams of carbon 12. Okay, so this is the standard, you need to remember that. Now, finding moles is super convenient, easy. For those who do not take chemistry, I just want to tell you that when you look at something, any element, right, in the periodic table, basically on that element, suppose that element is X, and it will have a number here, like oxygen has 16 and 8 as the 2 numbers. This number basically is the mass number. And generally, chemistry people call it as MR, okay? And this number is the atomic number, which is basically the number of protons in it, all right? So what you need to remember in physics is that moles, which are given by N, that's the symbol, is mass in grams divided by MR. So you can write it as M over MR. Is that clear, everyone? And you know what is MR? Like, for example, if it's 12 grams of oxygen, we divide 12 divided by 16. Is that clear? That would find us the number of moles. The other thing is that moles, other formula is number of particles divided by the Avogadro's number. So it is a fixed value. I'm going to just share it to you. So you can write, remember, is N equals to N upon Na. And obviously, this has a value of 6.02 times 10 raised to power 23. That is the fixed value of Avogadro's number. It's also given in your exam data sheet. Okay, so you don't have to remember it if you don't want to, but you should. Okay. Now, throughout this chapter, we will be finding moles again and again, and you will learn how to use both the formulas whenever required. But then the question is, what is meant by Avogadro's constant? And if this question comes, you're supposed to write that they are basically number of atoms in 12 gram. So So number of atoms is first mark, second mark is in 12 gram of carbon 12 element or isotope. All right, so you should remember that. That's very important. Anyway, now generally, the third definition, which is quite common, is the what is meant by an ideal gas. Now, whenever this definition is going to come, it could be like either 1 mark or it could be 3 marks. Okay, so I pasted the one definition with 3 marks because it also covers the 2 mark definition, so we don't have to worry about it at all. Okay, so the ideal definition for this is that you say that it is basically an equation that obeys, wait a second. Sorry. Ideal gas obeys the equation PV equals to constant. Okay, so this will give you 1 mark. That is a fixed equation. And now the second mark is when you explain what the symbol are, PV over T. Sorry. All right, and then you put the explanation like P is pressure, T is temperature, and V is volume. When you do that, you gain 2 marks. So for if the definition is of 2 mark, you just write these two. The third point is you have to explain the other things. Like you should understand that at all variations of P, V, and T, the constant is always the same as well as the mass. All right, so mass basically is something that doesn't really change, and you need to acknowledge that, although it is understood, but he would ask you for just for an extra point, and you should be able to write it. All right, so you can also write words like for fixed mass or something like moles are constant, something like that, right? So you should remember that. Anyway, so then you have two equations of state. These two will be required depending on, like, they are interchangeable, but it's easier to remember each one of them and then use them whenever a certain type of question is given. The first one is more common. So in this one, I just want to tell you this is pressure, this is volume, this is moles, this is molar gas constant. Molar gas constant is basically simply 8.31. Okay, you need to remember that. Okay, and obviously the last one is T, which is temperature. Now, this one is again pretty simple. Okay, I'm gonna take a different color. This is pressure. This is volume. This is number of particles. This is called Boltzmann constant. These all constants are given. So the value of Boltzmann constant is 1.38 times 10 raised to minus 23. And this is temperature. Now, one thing that I would like to point out, and you should write a note here, so you guys never forget this, and that is that temperature T is always taken in thermodynamic dynamic scale, which is basically Kelvin. Now, how to change scale to Kelvin? Although we're going to learn it afterwards as well, but temperature in Kelvin is taken as temperature in degrees Celsius plus 273.15. All right, is that clear, everyone?
Yes.
So please write it down. And these equations are your best friend for life till you're out of A levels. All right. Now, hello, Mokshit, Munib, Fahar.
Sir, what is the K in the second equation?
Boltzmann constant.
Okay.
Sir, you called me?
Sorry,
You called me like you said Mokshit. So.
I said hi.
Oh, hello.
Okay. Now, done. Should I go forward? Next slide.
In the previous question, state what is meant by ideal gas. You also mentioned something about moles. What were you saying?
I'm saying even if you write, you could say or. Let me write or. You could say at fixed moles. Okay. Let me write it down. At all values of PVT number of moles and are fixed or constant. Is that clear? So you can write in terms of moles or mass. It's the same thing. Okay,
Right, so
Javeria?
thank you.
Okay. So then we are gonna go to this one. And ideal gases are not exactly how real gases behave. And they have certain assumptions which we take in order to write them. Okay, so first of all, you should remember, first assumption is that the volume of ideal
It's
gas,
close to negligible.
yes, particle. Do not write ideal gas, right? Ideal gas particles, so this is a keyword, is negligible. Negligible. Oh my God, look at my spellings. Okay, negligible compared to the volume of container containing the gas. All right, so this is the most common point he's going to ask you, so you should remember that. The other point is that there are no intermolecular forces between them. Intermolecular forces, sometimes he would also use electromagnetic forces. So if he says that, do not worry, it means it is the same thing. Then the third point is the collisions of ideal gas particles are perfectly elastic. It means that they do not lose energy when they collide. All right. The fourth thing is that
They obey PV is equal to NRT equation.
no, that is
No?
basically the definition of ideal gas, not the assumption. Okay. So
Oh,
time of collision is negligible compared to time interval between the collision. which means that the collision should be like the time it takes to just collide and separate is so small compared to when they collide next time. All right, so that's the point. Fourth thing that you should remember, at any given time, there are always a large number of particles for statistical approximations to be made. All right, so that's how these 5 assumptions must be remembered always. All right.
So for point number 4, time of collision is negligible compared to time intervals, right?
Between the collision. Yes.
Yeah, okay.
It means that if A particle and B particle have to collide, so suppose they take 0.1 second to come to each other, right? So when they collide and separate, that collision separation should be like very, very small, like 0.0000000, maybe 1. Should be like negligible. Do you understand?
Yeah.
Yeah. Then in this question, it says, an ideal gas is assumed to consist of atoms or molecules that behave as hard identical spheres that are in continuous motion and undergo elastic collision. State 2 further collisions. So he has already given you the third point, right? So what you write? What would you write? You pick any two from above and write it here. Is that clear? Other than that. So the
Yes.
reason why you need to remember all of them. So because in this sort of question, you might be basically forced to write particular ones. Like, they might give you 3 and then they might ask you to write the other 2. And now if you don't remember the other 2, obviously you're gonna score 0 here. Do you understand? So this is why a bit of rote learning is required in this question. So to do this. All right. Anyway, although the other questions are very simple, I don't know what is this part doing here. Show that mass of one atom of, okay. So I just copied this. You can do this later. I'm going to do this for homework for later. But for the first one, I just want to explain it to you how we need to calculate the mass of a particle of ideal gas so that we can then go forward. So helium 4, they have given to you. Now, when you look at any element given as 4, 2, and whatever, you should remember that this is mass is 4U and the charge is 2E. 1U is basically 1.66 times 10 raised to power minus 27. We have done it previously as well. It's basically the 12th part of, like if you make 12 pieces of carbon 12 atom, and then you basically find the mass of just one part of that piece, it's this value. So then you can find 4U would be equal to 4 into 1.66 times 10 raised to minus 27. Now, the good thing about this software is that it doesn't keep on syncing every time, so I can use my calculator. And now I'm less dependent on Gatika and Joveria. So this means this is going to be 6.64 times 10 raised to minus 27 kilograms. And because he has asked you to find in grams, So we're going to multiply it by 1,000, and this will be equivalent to minus 24 grams, which is shown. Is that clear, everyone? Just like that. Okay. Any questions?
No, sir.
So the next part, we are going to do it like much later in the chapter. So you can come back and, do this again. Anyway. Now in this question, where did this question come from, by the way? I don't know. Is this the same question? No, it's a different question. Okay. So in this question, it says the container has a volume of 1.8 times 10 raised to a 4 centimeter cube. And the ideal gas in the container has a pressure of 2.0 times 10 raised to a 7 and the temperature of 17 degrees, which is great enough. And then it says that I want to show that the amount of gas in the cylinder is 150 moles. Okay.
So you have to find N.
Okay. First of all, yeah, we have to find N. So the best equation would be to use PV equals to N.
NR2.
Okay. Now, the issue with this question is that a lot of things are not in SI units. Like this one isn't SI units. This one is in degree Celsius. We want to convert into kelvins, right? So first of all, let's try to convert this. How do we convert centimeter cube into meter cube? Please learn this. So we know that 1 centimeter cube is equal to 10 raised to power minus, 1 centimeter is 10 raised to minus 2 meter. Everybody agrees to this? This would mean that
Yes.
if I cube on both sides, 1 centimeter cube will be 10 raised to a minus 6 meter
Yes.
cube. So I can replace 1 centimeter cube with this value. So pressure is 2.0 times 10 raised to 7. Volume will be then 1.8 times 10 raised to 4 multiplied by 10 raised to minus 6 equals to N. R is 8.31, and this is, I'm going to add to find in temperature in Kelvin. I will add 273 to 17, and I think that would be 300. So I'm going to write 300. And then simply just use your calculator. So 2.
Sir, don't we have to show the step that where we make N the subject?
No, you don't have to.
Oh. Okay.
Yeah, this is very simple. You can just directly do it. Don't worry about that. Okay, so 2 into 10 raised to power 7. Basically, it does not mean that I can now use my calculator so you don't solve it. It means you are solving it with me because also I can make some mistakes as you might have experienced before. So to do that, please work with me. Also, when you're writing on your own PDF, it is a good habit to use the calculator. So basically, it's
Sir, into you did divide
No, we got,
into
I got 149, sir.
You got
8.31 into 300. You did divide by 300
yeah,
on the
I've done the same.
calculator.
Yeah, it's the same thing. I have to divide it, with the answer. Why am I
Answer
getting
divided by
4?
8.31 into 300, right?
No, then you have to put brackets, If you do that, that would give you a wrong answer.
So won't we bring the RT to the other side? So it will be PV divided by RT.
Yeah, it's 290, not 300.
It's 290. Okay. If you
Yeah.
do 290, then it's 149. Yes, sorry. No, Mokshit, this is what I'm trying to tell you. This is where you need to also we always try to solve this. Like, for example, what you're saying is, if I do this, right, multiply by 290, it would give me a wrong answer, you see. So if you want to do it, then you have to put a bracket and then you're going to get the right answer because both values are dividing. When you write directly, it means 290 is being multiplied with answer. Do you understand?
Yes, sir.
Yes. So it means that now we got this, right? And then what else? So 29, it's 149, I think 0.4. So it's about the same. With two significant figure, it is 150 moles, right? So we've shown that. Now in the next one, it says a gas leak in the this has happened for some reason. I don't know why. But within that gas leak, we need to see that the gas molecules have a rate. So this many molecules per second are being released and the temperature remains constant in time t. The amount of gas in the container is found to be reduced by 5%. What are they talking about? What amount? Is this moles? This is moles, right? So it is reduced by 5%, which means how many are remaining? In time t, the amount of gas in the container is found to be reduced by 5%. Okay. So now the pressure of the gas after t. So it means 95% are left. You guys agree to this?
Yeah.
Yes.
Okay. If 95% are left, so can I say 0.95 times the original number of moles? And that is what? Go and find it.
142.5.
Eh? Sorry? 142.5
142.5.
moles. Okay, so you got the moles.
142.5,
Now,
yes.
yes, very good, very good, very good. And now, when you get this, we want to find the pressure, right? So we are going to use, again, PV equals to nRT. So we want to find the pressure. Volume would be the same because that is the container volume, which is, I believe, 1.8 times 10 raised to minus 2, right? And N will be now 142.5, R is 8.31, and we want to find temperature. Temperature is the same. So what you get?
1.9 times 10 raised to 7 pascals.
1.9 times 10 raised to 7 pascals. Do you guys understand the question now? Easy, right? Then in the next part, it says how much time basically it takes for it to do that, right? Now, the thing is that we need to understand that 5% of the moles have left. Okay. So previously
Sir, I have
our
a
moles.
question.
Yeah.
Sir, can you go to the previous question?
Yes.
I mean the previous bit. Yes. So here we calculated the mole as 149.4, right?
Mm-hmm.
So how did you
149.
make it 150?
Because it was the answer is two significant figure. So I converted it, right? So if you round it off, so it will be 150. No?
Okay, but no, I'm just asking because we got the answer 149.4. So how did you
Okay.
make it 150? Just because the question said you can round it off, or maybe there's uncertainty in our
No, no, you have to take this value. It's fine.
Okay.
It's all right. It's all right. Don't worry about that. Okay. All right. In that
Yes,
show
sir.
that question, even if you take that, it's fine. Okay. Then the difference in moles would be 150 minus basically 142.5, right? What is that? 7.5, I believe. So this is the amount of substance that left the container. You guys agree? Now we need to find the number of particles that basically left. And if the number of particles that are left how do we really find this? This is a question. Do we use moles to find it? Do you have a formula of moles that can help us find number of particles? You guys remember?
So moles into Avogadro's constant.
Yes, very good. So n equals to n upon Na. We can find n, and that would be 7.5 times 6.02 times 10 raised to power 23, right? Is that clear? 6.23. Oh my goodness. 6.023. Okay, can you please find this? Thank you. That would be very nice.
So 4.5 times 10 power 24.
4.5 times 10 power 24. Okay, 4.5 times 10 power 24. Now, ideally, yeah,
So
that's
these are
fine.
the particles.
These are the particles which has left. Oh, okay, sorry.
Yes.
Sorry. 4.5 times 10 raised to power 24, you said, right?
Yes, sir.
Particles. Now, they said the number of particles leaving was 1.5 times 10 raised to 19 per second. So 1.5 times 10 raised to 19 per second particle left. So how much time would that be? You just got to divide this. 4.5 times 10 raised to 24 divided by 5 times 10 raised to 19. Yes, what you get? 1 point or something. I don't know. It could be like it's almost
3.0 into 10 raised to 5.
3.0
Sec-
into 10 to raised to 43.
43. Why? Oh my God. Again, you're doing the same mistake. You have to divide by putting a bracket, Mokshit. You're basically doing
okay.
your. I just told you this. Now, this is a very common mistake. Don't do that.
Okay.
You get my point now, everyone? Any questions now?
So from
Sir,
where did you
I
get
put the bracket still. I'm getting
142.5?
3.0 into 10 to the power 43.
Yeah?
They're still getting the same answer.
I didn't understand. Come again, please. You guys were speaking all together, one by one, please. Yes? Yes, Mokshit?
So I
What do you
did the
say?
same. I did the same exact thing. I put the bracket as well, but I'm getting 3.0115 into 10 to the power 43.
How is that possible? That's not possible. Dekho, let me show you. 4.5 times 10 raised to power 24 divided by 1.5 times 10 raised to power 19. That's 10 raised to 5. Right here. The only way you can get the answer that you're claiming to be is when you basically write in your calculator something like this, divided by 1.5 and multiply by 10 raised to power 19. Then you're going to get this one, 45 one.
Yes, I did the same thing.
So why would
Answer
you do that?
divided by bracket.
You put a bracket here. Writing the bracket is so important because because otherwise your answer will be wrong. It's wrong BODMAS rules. Do you understand? Okay, yes, Gatika, what you were
Yes,
saying?
sir.
So from where did you get 142.5?
It was the moles that were remaining after like this time,
Oh,
So
okay.
I subtracted
Did you show the
I had initially I had this ones. Now this is the amount of moles left now in the container. So then 7.5 would be the ones that are gone out, right?
Got it, sir.
Okay. So I believe you guys understand this question. And now I got to go to the next one. So now there will be two types of questions in this. One question is a very similar question like this, where they say in a cylinder, volume of container is this one, helium gas, pressure, and temperature is given. And you got to find the number of atoms in this. Okay, number of atom means that we are looking for N. Now, which formula should we use? PV equals to?
So number of helium atoms, so NKT, right?
So PV is equal to NKT, right? So this is how you're going to decide which formula. You can use the other one as well. Even if you use this one, that is not wrong, but then you will get moles. And when you get moles, then you have to again use N upon Na to find the number. So that would take more time and more effort, and please don't do that. Anyway, so now it's basically 6.4 times 10 raised to power 6, and the volume is 1.8 times 10 raised to power 4, and I'm gonna basically replace centimeter with -6 meter cube, and n is n. You just need to remember it's 1.38 times 10 raised to power 23, and then this value you add 273 to it. So
So it's power
273
-23, right?
negative 23. Yes, sorry, like that. Okay. Yes, please. Can you please find the answer?
2.8 times 10 raised to 25.
So 2 point
8.
times 10 raised to 25. Okay, can you guys please confirm the answer? I don't trust you people, nor myself. That's fine.
Yes, sir, it is 2.8 times
Okay,
10 to the
very
power
good.
25.
Anyone who did not understand this, do you now understand both the formulas and when to use them? So it is basically easier that way. Anyway, so now going to the next type. This sort of questions I really love because they're much easier than the ones we've just done. In any case, it says that a fixed mass, blah 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 blah, and says determine the amount of gas. And you guys know that this is basically the amount, right? So again, you have the pressure, volume, and this, and amount of gas is basically N. So you'll use PV is equal to N RT. And 3.0 times 10 raised to 5, volume is 210 times 10 raised to -6. And N is what we need to find, 8.31, and the temperature is already in kelvins, thanks to them. And what is N then? 3 marks for this. Oh my God. This is unfair,
0.028.
Easy marks.
0.028.
028.
So this is unfair to so many people. So easy. All right. Anyway, now this sort of question where it says the final temperature T of the gas. Now what you want to do? If they have like the similar gas with two different conditions, so you already know that all these equations, basically it is nRT or PV is equal to nKT. NK and R basically are constants. So you can always remember, you can remember as P1 V1 over T1 is equal to P2 V2 over T2. So just remember this for comparison question, okay? For same gas at different conditions. So this will really help you solve the questions very quickly. Now what you're going to do is you're just going to add things into this. So the first pressure was 3.0 times 10 raised to 5, and the volume was 210. You don't need to convert anything. The answer will be in whatever units is the one that you're finding in. And the temperature was 270. In the other condition, it was the same pressure, different volume, and different temperature. Can you quickly find this, please?
Sir, can you explain why NR and NK got removed in the equation?
Yeah, I'll tell you. Just hold on. First, find the answer, please.
So 180 Kelvin.
180 Kelvin. So that's the answer. Now, I'm just saying ideal gas equation is PV over T is equal to constant. This is the definition of an ideal gas, that it obeys this value. Do you agree?
Yes.
This constant could be, in chemistry, it is Nr. In physics, it is Nk, right? These two are the same things, actually. Do you understand?
Oh, okay.
Okay. So
Yeah.
if Nr for the same gas or nk is the same. So in the other condition, if one of them changes, then we can compare the other condition like this, because this and this will always stay the same for the same gas.
So
Do you
it's like
understand?
P1, V1 is equal to P2, V2, something like that.
Yes, exactly. This is the same thing. But now, because
Okay.
in A levels we also consider temperature, so now it becomes PV over T. All right.
Understood, sir. Yes, sir.
That's what I'm saying. Always for any gas that you're comparing, the same gas in 2 different or 3 different conditions, you are supposed to take this ratio. You don't have to solve it again and again. That would take a lot of time. Don't waste that. Okay. All right. Now, so this is the type 2 question, and obviously I hope you guys understand this. Arsalan, Munib, Nadia, Suman, Tanjim, everything
Yes,
is
sir.
clear. Aman, Fahar.
Yes, sir.
Yes,
Everything's
sir.
clear. No doubt.
Yes, sir.
Fahar, none of your work is submitted. That's not good. Please submit your work. Now, then I've given you some practice questions. You will do it on your own. So these are all homeworks. This one, and we're gonna start from here now. Okay, so we got 20 minutes, and within those 20 minutes, we got to do a lot. Now, this derivation is very important, and this is the derivation for the equation PV is equal to 1 by 3 NMC squared. The whole definition or some part of it might come in your exam, and there's no saying what will come. So you should remember that. First of all, we're going to look at this container. Usually this container and the shape is already given to you in the exam, so you don't have to worry about that. But we start this derivation for just one particle, okay? Now, so for just one particle, I would like to tell you that it is when the particle goes from B, hits A, and back to B. So this is like one like whole oscillation, right? So this like goes back and goes back like that. So within that time, the first thing is you're gonna find the change in momentum. If it's going in this direction, I've written it as minus ux. Okay, you can take it otherwise as well, and it has mass m. So the change in momentum, you've done it in AS, which is final momentum minus initial momentum. Final momentum is going to be when this particle would actually move backwards and with the velocity of ux. Why ux? Because in ideal gases, we have learned that all collisions are elastic, and that means that basically you do not lose any kinetic energy. Anyway, so final momentum will be m times ux minus m times minus ux, right? So this is going to be mux plus mux, and then you're going to get 2mux. Any questions up till now, please let me know. Okay, then
So what's UX?
the ux is the speed in x direction. Understood?
Okay.
It's like u and x is in subscript. It's not being multiplied to you. Okay, it just
Yes,
says
sir.
that
Yes.
in x direction. Okay.
Understood.
Anyway, then the next thing you're gonna do, so I'm gonna change the color. I have unlimited colors, so I'm gonna use the next color is this one. So you guys remember. So then you're gonna find the time interval between successive collisions, which is basically when you go from B to A, collide at A, then from A to B back, right? So it's like this. And then again, the same path again. So when you do that, you go from here. So the time you take is basically dependent on the distance you travel, and the distance you travel is from B to A and back to B, which is 2 times this distance that I've written on the top. Is that clear? Divided by
Yes,
the
sir.
speed. the speed is ux. Okay.
Yes, sir.
So I would say this is equal to t. Then basically this basically causes a force, because we have learned previously that force is sort of thing which is basically, we would say the average force that acts on A would be something like, this color is not very good. Wait a second, let me make it darker. All right. So force is given by change in momentum over time. The change in momentum was 2mux and the time was 2 times d over ux. You guys agree? Please have a look at it.
Yes, sir.
So ux is going to go on top and 2 and 2 will cancel out. So this will become mux whole square divided by d. So this is the value of force. Okay. All right. Then, so right now what we're doing is we're only doing it for one particle, right? But they're not one particle, they're unlimited number of particles, right? So for n number of particles, we would basically do something else. For now, what we're doing is we are basically assuming few things before we go to our final conclusion. We're assuming that all particles hit in same direction. Okay. And the other thing is that all particles have the same speed. This is our assumption. And the third assumption is that there are n number of particles, right? So we are writing like this. Is that clear, everyone? Now for
Yes,
that,
sir.
we should first understand that we can actually find the total force exerted on A by n number of particles. This is now what we're finding. So because just one particle has this much force, so n particles will have, like I can say, force total would be equal to n times the force of just one particle. All right. Then the last thing in one-dimensional movement we're going to do, let me change the color. Total pressure what? Okay. Total pressure on wall A. So pressure is given by force over area. The total force was nmux square over d, and the area of this was simply, let's say this is the area, so we'll call it area A. All right, is that clear?
Yes, sir.
If you see, this is nmux squared divided by area times d. D is this length, and area is the surface area of this. What does that make it? The volume of the container, no? So we can write it as nmux square over volume, where this is the volume of container. Okay, understood?
Yes, sir.
Now this is the pressure. Now this whole thing is based on a poor assumption. And the assumption is wrong because in reality, any particle moves in three-dimensional space, which means it has x direction, x vector of its velocity, y vector, and the z vector as well. Right now, we have only solved it for just one dimension, and that is not correct. Is that clear? Hello, Isa.
So we're going to apply this to all three directions, is what you're saying?
And now in the next part, we're going to apply in all directions. Okay. Hello, Isa.
Hello, sir.
Isa, please do not be scared. Okay. I'm just finishing up. Okay. All right. Okay. No, physics, it doesn't look that hard. Okay. It looks hard, but it's not, Isa. Okay. In future. Okay. Then. Huh? Isa. Okay. Now, we're going to apply this on our third dimension, and obviously they move in all directions. So in a 3D vector system, like this is a 3D vector system, we should understand that you cannot simply add velocities like 1, 2, 3. Okay. So what you do is, suppose if you have, there is a velocity, the speed of that particle in y direction, and then speed of that particle in z direction, x direction, and speed of that particle in z direction. So previously in AS, you might have learned this, that when there were two vectors which are 90 degrees to each other, y and x, you would simply use Pythagoras theorem. So you do y squared, x squared, and you get the resultant. Remember? So this was only for 2D. In 3D Pythagoras system, we have to find the square speed, and that would be in x direction square plus y direction square and the z direction square. Do you guys understand? So this is basically the square speed, which is basically known as c squared. So let me write here square speed. So basically what I've done is I have found the resultant speed of any particle moving in the 3D space. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now, the reason why we need to square it off, because we used to square vectors to remove their vector attribute, which means a vector cannot be simply added like this. It needs to be squared first so that the minus positive sign doesn't matter anymore. And then you can add the magnitude, and that is why we're squaring it. So this c squared is for just one particle, but if I want to find it for all the particles, right? So what I can do is I can find the mean of square speeds, okay, of each direction. Now, let me just explain it this way. So how do we find the mean? You say in this x square of mean of all the particles moving in x direction would be the first particle in x square, like x1 square, and then I'm going to add the second particle speed in x dimension, the third particle speed square, and I will do it for n number of particles and divide it by the number of particles that I have. This will give me the mean speed of all particles in x direction. Do you guys understand this? Similarly, for y direction, I'm going to do the same. I'm going to find all the speeds of each particle in y direction. I'm going to square them up to remove the vector attribute. And then I'm going to add them up and then divide by the number of particles to find the mean speed of all particles in y direction. Is that clear?
Yes, sir.
Finally, I'm going to do the same with the Z1. And I'm going to u z1 square plus u z, the second particle speed, the third particle speed, and no matter how many particles are there, and then n number of particles, I'm going to get all the mean square speed. Now, now, the only thing that is left, and that we need to understand this very, very important factor, and that is that this speed that we have just found, this thing, we need to remember that the mean square speed of all of them, all right, all of them, basically is sort of, I would like to tell you that it is equivalent to something like square speed of all of them in x direction, in y direction, in z direction, right? Like that. And the assumption that we take here, which is very precise because almost it is very true, and that assumption is that the mean speed of all particles in x are equal to mean square speed of all particles in y direction, and this is all particles in z direction. So this is very true in the actual sense as well. If you really want to learn more about it after your exams, you can always look at the Maxwell distribution curve. Well, nobody will do it, but if you want to, you can always look at it. Anyway, so going to the next part. So according to this, then it means that all of them, if all of them are same, can I write this as c square is equal to 3 times of cx square? Can I do that, please? Okay. Now, just remember the last step that I'm going to do, and then we're going to finish the class because this is like Isa is waiting. Isa doesn't like to wait. Anyway, so in according to our previous one, in one direction, we learned that P is equal to Nm ux square over V. This was the pressure. Now, ux was just for one particle in one direction, but if you're talking about x speed of all particles, we can write it as P equals to Nm Cx whole square. So this is mean speed of all particles in the x direction like this, right? Now, what I'm going to do is I'm going to multiply V on the other side. So it's going to be PV equals to Nm Cx square. And then because I know that Cx square from this part can be regarded as 1 by 3 c square. So I'm going to replace this right here. Okay. And if I replace this, then it becomes PV equals to Nm 1 by 3 c squared. And that's how I got 1 by 3 Nm c squared. And that was the basically goal of doing all this. All right. Is that clear, everyone?
Sir, I just have
Okay.
one question.
Yes, please.
Are they gonna ask like a 10-mark question of me writing all of this inside the exam?
Yes, they will do it.
Oh Lord.
Okay, so pressure, volume, number of particles. You want to see something cool, Javeria? Mass of one particle and mean square speed. Okay, so this is this. Okay, so the last thing before we have only 2 minutes left. So now, because you've learned this, you're gonna go here and you're gonna basically you will not do this question. I'll do it tomorrow. But basically, what I want you to do is I want you to solve this question on your own today, like after the class. And this question is the same that we have done. And how many marks are this? 11 marks. Happy, Javeria?
Not exactly, but okay.
So
Okay,
can you show
so
the
this
previous page real quick?
All right, is that clear?
No,
So you have
when
to
we
do
were
it
doing.
today so that once you have done it, you guys can,
Yeah, okay, thank you.
you have. Yeah. So this whole derivation is a part of exam, and I'm telling you some part of it, and the question I've just shown you, all of it can come in the exam step by step. So that's fine. Okay then. All right, everyone, time to go.